Ever heard the phrase correlation does not mean causation? You probably did, but what does that actually mean? In this video, we're going to look exactly at how correlation is different from causation. We're going to learn how to do this in R. By the end of this video, you'll feel confident about the relationship between correlation and causation, and you'll also feel confident about how to measure the strength of the relationship between two variables. Why should you trust me? My name is Bogdan Popescu, and I'm an assistant professor of political science at John Cabot University of Rome. I also used to teach at Oxford and at Princeton. I have years of experience of teaching statistics, so let's dive right in. Okay, today we're discussing modeling relationships between variables. We're going to discuss the concept of correlation, how to do a simple linear regression, and how to interpret a regression outcome. So it's important to define what a correlation is. A correlation coefficient is a type of statistic that measures the strength of the relationship between two variables. So previously we discussed the case of urbanization life expectancy. We noticed that typically there is a positive relationship between urbanization and life expectancy. Another way of saying this is to say that places, countries that have a higher levels of urbanization also have higher levels of life expectancy. So this is a graph that shows exactly this. So on the x-axis, we have urbanization average, and on the y-axis, we have life expectancy. This is based on the data sets that we used previously. These are life expectancy and urbanization from our World in Data, which also take their own data from the UN. So this is displaying this graph after merging the data, after calculating the averages by country. If you want to learn more about how we did this, I encourage you to watch the previous video. But I also included the code here. Typically, we first load the data sets. So this is what happens in code in line 5 and 6. We're just simply reading the CSV files. Then we calculate life expectancy and urbanization by entity and by code. So this is in order to keep both the name of the country, but also the 3-letter code. We get rid of some weird labels, so the missing 3-letter codes for some countries, and then some countries have more than 3 letters, we get rid of them. For both life expectancy and urbanization. Finally, we do a left join where all the places or all the countries in urbanization get merged to the countries that have life expectancy. We get rid of missingness, and we finally plot the data in order to create this. Once again, in order to figure out how to load the data and where to download it from, I encourage you to go and watch the previous videos. So, moving on to what I just said. So there is a positive correlation between urbanization and life expectancy. If we actually calculate this correlation, we will get this number. So this number is obtained from this simple line of code. COR, this is the final merged data. This is life expectancy. And this is our measure of urbanization. So the correlation between this variable and this variable is 0.63. So I included here once again just how to load the data and how to obtain the final data set, this one, merged data. So this illustrates that there is a positive connection between urbanization and life expectancy. The formal definition of a correlation or Pearson correlation coefficient is this ominous looking expression. So what does it mean? So this is a Pearson correlation coefficient that describes the strength, but also whether the relationship between two variables is positive or negative. So let us look more carefully at this formula. So small r represents the sample Pearson correlation coefficient. So there is a different symbol for population correlation. So that will be a rho, but we're not covering this in this lecture. X and I are the values for the variables X and Y. Notice here that the values are noted or are written as lowercase x and y, whereas the variables are written with uppercase x and y. X bar and y bar are the sample means for the variables x and y, and n is the sample size. So this is what we had here. Finally, Sx and Sy are the sample standard deviations for x and y. Once again, to learn how to calculate the standard deviations, I encourage you to watch the previous video. Okay, it's important to note that just because two variables are positively or negatively correlated, that doesn't mean that they're also causally related. So it might be tempting to say that, yes, increases in one variable cause increases or decreases in another variable, but this is problematic for three important reasons. One, we do not know the direction of causation. We do not know whether it's X that produces changes in Y. It could also be the case that Y also affects X. This is called reverse causality. There could also be a third variable Z that affects both X, both Y, or both X and Y could be measured with error. All these three problems prevent us from making the case that X is causally related to Y. So all these three problems suggest that we have what is called endogeneity in the relationship between X and Y. So the big lesson here is that correlation does not imply causation. Okay, moving on to how to calculate a regression coefficient and how to plot a regression line. So we typically make predictions with the help of regressions. So a simple regression can be written as this. So yi hat is equal to bxi plus a. So what does this mean? Xi are the individuals, so xi hat, so this tiny circumflex, so this tiny hat is read as predicted values. So we have the individual predicted values on the dependent variable, and xi is the individual value of the independent variable. This is very similar, if you look at it carefully, to the simple linear equation in mathematics. So y is equal to mx plus b. So just a reminder, m is the slope. So this tells you how steep or how flat the line is, whereas the b is the y-intercept. Okay, so this essentially means where that line starts from. So if we take the urbanization and life expectancy example, we know, for example, that the mean of urbanization is this value. So once again, to figure out how to calculate this, I encourage you to go to the previous video. This is the mean for life expectancy. So y bar is equal to 61.259. The standard deviation, Sx, is this. So xi, the sum of sort of deviations, right? So xi, remember, is the individual value for big X. X bar is the average X. N is the sample size. And then we square this and we take the square root. So this gives us a standard deviation for urbanization of 24.18. And then SY is the standard deviation for life expectancy. So the same sort of calculation, but now we're using Y. So the standard deviation for life expectancy is 8.64. Finally, we put all these numbers into the formula, we plug them back in, and this is going to give us a correlation coefficient of 0.63. Okay, we can then plug in these numbers in order to obtain the following statistics. B, the formula tells us that B is equal to R, which is the correlation coefficient, multiplied by a fraction between the standard deviation for Y and the standard deviation for X. So if we plug in what we just calculated, we get 0.63. So this was the correlation between X and Y. And then we have the standard deviation for Y and the standard deviation for X. This is going to give us this number, 0.22. Okay. In practice, we get this number just by doing this in R. So this is a simple linear regression in R. So this is the data set that we're using. This was the final merged data set. This is the dependent variable, so life expectancy, and this is the main independent variable. This symbol here, the tilde sign, is really equivalent to equals, but the way you indicate the dependent and independent variables in R is by using this tilde sign. And then LM stands for linear model. I'm saving this as a knob called X, and then I'm using a function called summary that allows me to see the output. So once I use this and run this model, I get this. Do you see how this number is the same as this number? Right? So we never need to manually calculate the standard deviation, the means, anything like that. We simply could just run this simple line, which is going to give us the relationship or the strength of the relationship between urbanization and life expectancy. So we can also plot this slope, so this 0.225 in the following way. So remember, this is B. This is how steep this relationship is, meaning as urbanization increases, so does life expectancy. So the fact that we have a positive slope suggests that we have a positive connection between the two. I included here the code so you can clearly see how to create this graph. This is a simple scatter plot that's created in the same way that we did before. What's different here is the label, right? So adding this blue annotation here on the left-hand side. So the question here, what would happen if this was negative? I guess this is much clearer now what the slope does. So this was a positive slope. This is a negative slope. Notice here that this is minus 0.225. So our slope, if the B was negative, we would see this type of line, right? Clearly, our data does not suggest a negative relationship between urbanization and life expectancy. But once again, to visualize what the slope really is, that's the point of it. Okay, the next step is to calculate the A, or alpha. So the way we do this is by calculating this. So alpha is equal to y bar minus beta, or minus bx bar. So we calculated, we know what is the average life expectancy. So y bar is 61.259. We calculated the beta, and then this is the x bar. So this is the average urbanization. We do the algebra and we get to this value. A alpha is equal to 49.69. So what does this really mean in practice? This is what this means. This is the starting point of the B line of the slope, right? So I marked it here. This is this precise point, 49.698, just slightly below 50. So this is what alpha represents. It's really the starting point for the line. Knowing the value of A and B, alpha and beta, we can use them in order to calculate predicted values for Y. So remember that this sign with this, it's read as predicted value of Y, which is equal to beta xi plus, so this is going to give us this number multiplied by xi plus 49.69. These are numbers that we calculated. So this is something that we calculated a few slides ago, and this is the alpha or the A, which is what we just calculated. So the only thing that we're missing is the xi, which are the individual independent variable values. So this is what we get. These are the red triangles are the predicted values for yi. So the gray dots are really the black dots from before. So these are the actual observations for both x and y. The red triangle now, the red triangles are predicted values for yi. So we can now calculate the residual. So what is residual? This is really the difference between the actual values of y and the predicted values of y. So you can clearly see in this example, this is a negative residual. So our original data for y indicated this value for life expectancy. So I guess that should be around 52 or so. But then our model predicted maybe 62. Let's say it's 52 plus 13. So that would be 65, right? So we overpredict. So in this case, we're getting a negative residual. So the difference between the actual value for y and predicted value for y is called a residual. Okay. So I'm repeating myself here. So there is a difference between yi and yi. So yi is the observed value for life expectancy, whereas yi hat is the predicted value on life expectancy. So we can obtain the yi hats by plugging in their x value into the regression equation. So fundamentally, the regression line, blue line that we just observed here, is really the type of line that minimizes the size of these residuals, right? So this regression line tries to minimize these errors. It tries to make them as small as possible. So this is why sometimes the regression line is also called the line best fit. Okay, so once again, this is how we run a regression in R. So this is the data set that we merged, the final data set. This is X, and this is Y, right? And then we simply run a linear model, and then we summarize it in order to see the A, the intercept. Remember this number, 4969. And also, here is the B, beta, 0.25. And also create a table. So this table shows us the main B. It shows us the alpha, the A. It also shows us some important statistics, such as the number of observations and the R squared. So how do we get this table? We simply run the model once again. We add a list here where we essentially give a name to the model. As you might imagine, this is responsible for this text here. Then we replace the X labels and the Y labels with these labels so that we can nicely see values such as urbanization or interest. And then these additional things here allow us, for example, to plot stars. And I'm going to explain in a few slides what these actually mean and why they're necessary. And then I'm also explaining what are the type of additional statistics that I would like to have displayed in this table. So those would be NOS. So this is number of observations, and R squared. Okay. We can also display our results in a plot. So notice that we still have the same X, and so we have the same B and the intercept. So here's how I obtain this. So first of all, I'm loading this library. It's called Brew. Second of all, I'm rerunning the model, but I'm doing something different here. What am I doing? I am scaling the variables. What does this mean? I'm subtracting the mean and I'm dividing by the standard deviation. But there's no need to manually do this. I can just use this function called scale. So the reason why I'm doing this is because sometimes you end up with coefficients of very different magnitudes. So in order for my plot to look like this, so that we can see confidence intervals, these lines here for both coefficients, it's important to be measured in the same scale. So this is why I'm using the scale function in this line of code. I am saving the model. I'm using this function called tidy that comes from the Broom library, which allows me to save this model as a data frame. I am now changing the names of the variables into urbanization and intercept, opposed to these variable names. And finally, I'm using ggplot. So this is the result, the data frame. The x-axis has the estimate, and the y-axis has the term. I'm then creating error bars. So I'm essentially subtracting from the estimate 1.96 multiplied by the standard error. And then I'm just adding a few additional aesthetic choices for my coefficient plot. So finally, the coefficient plot looks like this. So the table and the plot tell you exactly the same story. It's really up to you to decide how to interpret. But back to the table. So how do we interpret this table, right? So we learn how to plot it, how to create this table. How do we interpret it? So here's the interpretation for urbanization. The correct interpretation is the following. For every 1 percentage points increase in urbanization, remember urbanization is measured in percentages, the model predicts an average increase of approximately 0.225 in life expectancy. So given that life expectancy is measured in years, you can say that 1 percentage point increase in urbanization leads to 0.225 years of life expectancy. So this is a statistically significant relationship. So how do we know this? It's because of these three stars. Remember that I mentioned to you earlier, I drew your attention to these three stars. When you see three stars alongside a coefficient, this means that this coefficient is statistically significant at conventional statistical significance levels. So this would be 0.1% in this case. So this is what the three stars mean, a p-value that's smaller than 0.001. The standard error is this. What you would typically see in a statistical analysis table is a coefficient and a standard error between parentheses. So this 0.019 means that it tells us how much the estimate would vary across different samples. So the smaller the standard error is, the better, the more precise our estimate. Okay, finally, the intercept, remember that we calculated this 49.69, is really the A, the alpha. So what does this mean? This means is when urbanization is 0%, the predicted life expectancy is 49.69 years. This is how we interpret the intercept. So, of course, in practice, this may not be always meaningful. In this case, it is, right? Or to some extent. Or maybe if we think about it, it could be the case that no country has 0% urbanization. But this allows us to make calculations, like what is the life expectancy for a country that has 50% urbanization? What about a country that has 30%, and so on and so forth? The reason why the A is useful is because this allows us to make predictions. Okay, finally, how do we think about this symbol, r squared? So we got an r squared of 0.397. So this number here, this number tells us the variance that is explained in our outcome variable by the predictor variables. How much of the variance, the dependent variable, is explained by our independent variable. So in this case, we say that our model explains about 39% of the variance of our outcome variable. So our model explains 39% of the variance in life expectancy. So typically the R squared ranges between 0 and 1. If R squared is equal to 0, this means that no variance is explained. If it's equal to 1, that means the entire variance is explained. We now have the following notation. So y hat is equal to bx plus a. This could also be written, so in some academic articles you might find it like this. So y hat is equal to alpha hat plus beta 1 hat x plus epsilon. So this is why throughout this explanation I kept mentioning both a and alpha and both b and beta, precisely because of this. Or you might also find notation that looks like this. Instead of alpha hat, you might see beta 0, but epsilon is it's called the error term. So I wrote here once again. So alpha is equal to A is equal to beta 0, B is equal to beta 1, epsilon is the error term. Okay, we have covered quite a few things today. So we looked at correlation. So correlation is really the statistic that quantifies the strength and the direction of the relationship between two variables. Regressions help us model the relationship between two variables in order to make predictions. We learn how to calculate the slope, b or beta, which tells us the expected change in the dependent variable for 1 unit change in the independent variable or the predictor. We also learned how to calculate the A or the alpha, or in this case beta 0, which gives us the expected value when for the dependent variable when the independent variable is 0. We also learned that r squared measures how much of the variation in the outcome of interest is explained by the model. And probably the final most important lesson here is that just because two variables are correlated, that doesn't necessarily mean that they're also causally related. Thank you, and see you in the next video. I hope you enjoyed this video. If you found it helpful, please give it a like and press subscribe. Also, if you have any questions or comments, feel free to leave a comment down below. Thank you, and see you in the next video.